Hello and welcome back to differential equations. I'm going to use my radio voice. No, I'm not. So first exam, you said that it should be chapter 1 plus chapter 2, which is 2.1 including 2.4 or 5. I know it starts with F. 4? Okay, good. So this is what we have for the first exam. And it's going to cover all of the concepts that we discussed. So we are talking about, the exam is geared to be hour and a half, because usually exams are supposed to be hour 20. You should be able to complete everything in an hour with 20 minutes of check time, and then you hopefully remember that each differential equation, when you have a solution, you can differentiate, plug back in. If the problem says solve and check procedure is going to give you the points. If it just says solve, if you do the check, there are no points, but then you know that. Did anyone bring tear gas? Thank you. So if the problem says solve and check, you must check if you want the full credit for the question. If the problem says solve, well, if you're mature enough, you will check. If you're not, you're just gonna hope that you did it right. All of the check procedures in this class are the same. You will take appropriate amount of derivatives, plug it back into your original equation, and you either have the answer or something is wrong. If you're not getting the exact answer, what you should do is first check the check first, and then if that all looks okay, because your check is usually a few lines rather than a problem being half a page or a full page. So check the check, and if that checks out, then you can go back and, depending on how much time you have, you might redo the problem, or you might try to find your mistake. It's difficult to find, thank you, it's difficult to find your mistake. Might be better off redoing the problem quickly, because you already know what the steps are, what steps are included. It's just grinding through the problem. 100 points. Depending on spiciness of the exam, I might have something that's called a replacement problem. Replacement problem is there to replace any problem on the exam if you need to, if you can't remember a certain concept. Replacement problem is only graded if you write which problem you are replacing, and then that other problem is not graded at all, whether it's right or wrong. If you write replace any problem that it's wrong, I will burn the test, the entire test.
So can you make up a new problem for the replacement problem? Or?
It will be on the paper, like all other problems.
Okay.
Yes. Like you should know that. 100 points for the exam. The number of questions really depends on the procedures. The lowest amount of questions that I've ever had on differential equation exam of any kind was 6. And the highest amount of questions was 10 for the regular exams. We can have a problem here that would literally take 2 minutes to solve with constant coefficients, homogeneous, right? Let's say repeated solutions or whatever. That should literally take you 2 minutes. You write a characteristic equation, you factor it in your head, you write down the solution looking at those roots. So that should take 2 minutes or less. So you have those types of problems. But then you have the other types of problems, like exact equations, which take almost a full page. So, you know, you can't expect 10 points for the right exact equation and 10 points for constant coefficient second order non-homogeneous constant coefficients. I think I said that, and whatever. So there is some balance there, anywhere between 6 to 10 problems. 100 points for the exam. The first exam counts the least of all exams for you to get used to differential equations. Also, to check how well you're managing your study time versus all other time. If you're investing enough in the class in terms of hours spent in practicing these things. I already asked you 15 times to classify differential equations on a sheet of paper, to maybe write the main formula and then to write an example next to it so that you can start as soon as possible learning the names and the forms of these equations so you can quickly spot, oh, this one is constant coefficient second order. Oh, this one is going to be separable. Oh, this one is integrating factor. Oh, this is exact equation. So when you start classifying equations like that, and you should actually, I mean, I did mention this a month ago, first time. I mentioned this right after we did exact equation for the second or third time, actually, where we had 6 different types at that point. Certain methods will upgrade, like the one that we are doing now for the next exam, and certain concepts are completely new track. So, modeling, which is word problems, that should also be there. We'll take a look at some of the models, say for predator-prey models for population. Can also think of some of the velocity models. Problems could be either translate English into mathematical equation, solve it, or could be derive this formula from that formula, which is simply a calculation. So let's see what are the things that we are considering for the exam. We start by ODE classifications. So classification is the first one: linear, nonlinear, homogeneous, non-homogeneous, constant coefficients versus non-constant coefficients, first versus second versus third order, right? Order of differential equation. So you have all of these classifications that are that we had in the beginning and throughout these few sections. So classification is first, to know how to deal with this. And then we have the concept of general solution versus particular solution, where you need to be able to use initial condition to solve differential equations. So I'm just going to call these solutions. And solutions of ODEs, ordinary differential equations. And solutions means general solution versus particular solution, where you also have the initial condition to compute. Then we get to separable equations, then the first order linear. We have integrating factor. Then we have, what else? Integrating factor, and then we have substitution. That's the bad one, right? And then we have exact equations. Why? Go away. There we go. Exact equations. which is the procedure. And then we have modeling, which is word problems. And those go into population. They go into motion. And they go into one more. No. The mechanical vibrations. First two are from chapter 1, and the third one is the chapter 2. And we have the second order linear ODEs, constant coefficients, which contain, right, reroots, repeated, and complex, which all lead to their own solutions. I know I forgot one thing. Slope fields. There we go. This should be all the way up on top. So for the first order, is it a slope fields or yeah, it's no slope fields. Anything else that we should add?
No, that was pretty good. You guys give us stuff all those problems.
Well, he doesn't do all of them. He doesn't, yeah, but
No, yeah, it's really fun.
just they can all end up on it.
Yeah, but when you take a look at this, right?
3 things that you won't follow.
Well, yeah.
Please
So let him speak. Solutions to ODEs will be actually present at each one. Oh, I have to add this. I'll add this in red. Check your answer. So, classification, solutions, separable equations, first order, linear, integrating factor, substitution method, exact equations, modeling with word problems, second order, ODEs. So technically, these are molded together, right? Actually, not second order, higher order. And then constant coefficients is the higher order, because we did the last time in class we did the fourth order, right? So yeah. Now, most of these things are procedures. You know how to do this stuff. Generally, what I found with the differential equation exams is the issue with integration, issues with algebra. Those are the worst kind of issue, the algebra issue, right? I don't know, this was some time ago, maybe 3-4 years ago. I taught a differential equation class. It was in the summer, so 3 or 4 years ago. And on the exam, I dared to write solve y triple prime minus y equal to 0. So that was the equation. And what type of equation, so where does this fall on the list of things we just talked about? Higher order linear equation, very good. And what do I do with this? How do I solve those types of problems? Characteristic equation. What is the characteristic equation for this? R cubed minus 1 equals to 0. Now what? I factor this. Great. What are the factors? Yes?
R squared.
And this is where the differential equations die. At the algebra. What? What? Yeah, R equals 1, but this is a third order. What are the other two solutions?
We try to use negative b plus or minus the quadratic or no?
That's a cubic over there.
So you just do r squared minus 1
Nope.
Now you divide all minus 1 and then into the.
Yeah, so he is going to give us correct answer, but that's actually driving through RV through Holland Tunnel every time you have to come here. Because he knows the root is 1, so take this and divide it by r minus 1, and then, sure. But see, if you know algebra, this problem is very simple. Exactly. R minus 1, and then very close to what you suggested, r squared plus r plus 1. Good.
So is there a way like
There is a way. Ryan gave you the way. Ryan gave you the way. He said divide r cubed by r minus 1. You do the long division of polynomials. If you don't know how to factor a cubic difference of cubes, which is a formula, then you would have to. Now, this was the problem on, right? But you have the fourth and the fifth, and right? So somehow, see, the issue is generally you can't perform algebra and everything falls apart. So now, r equals 1, and over here you have your negative b plus minus b squared minus 4ac divided by 2a, and you see that you have now negative 1/2 plus minus root 3 over 2i. So there are your roots, and you can find the solution of y of, say, x or t, whatever, is going to be c1 e to the t, no, e to the x, because we picked x, plus e to the negative 1/2 x times c2 cosine of root 3 over 2 x plus c3 sine of root 3 over 2x. It's a 4-line solution. Handful of students got it because couldn't deal with this.
Are you going to put a lot of hyperbolic cases inside?
Now that you mention, I should, but I can't because we haven't done much with them.
I know like during the homework, I informally learned.
So you can informally learn them. So, but yeah, they spring from these types of solutions. So, I mean, is this a request?
No,
Okay.
nothing's requested.
Nothing's request. Give us more hyperbolic functions. Sure. Secant hyperbolic. Inverse. And that's the review. We're done.
Nice video.
Right? Yes. I hope. I don't have a book though.
Many problems.
Yeah, can you do one problem? It's a problem 3 on page 9.
How about we do one big substitution problem and then you take care of everything?
What if we do though?
The whole exam, one problem. Dow disagrees.
Are you going to substitution problem? And will it be?
And will it be spicy?
I mean, I would definitely not like to get burned out of dust.
You want the solution for it then? Yeah, why would I use the solution? Can we write the exam with you?
Actually, it is.
Yeah, I feel like there's a
Yeah, there's no. Yes and no, Alex. Problem 3 on page 98. What the hell is this? xy plus y squared minus x squared y prime is equal to 0. Is that the one? Yeah, we got, so what I would do is I would first write this as x squared y prime plus xy plus y squared equal to 0. And then I would try to, well, I would divide by negative x squared to see if I can get anything that it's manageable over here. So when I divide by negative x squared, I get negative y over x minus y squared over x squared equal to 0. What should we do now? Y over x. U equals y over x. So we should try v. We can use u. Oh, fine, we are using v. Because we see the structure, right? Y over x. So it's not stated use exact equations, use separation of variables, use substitution. It just says do it. And from the list above, you have all of the methods, and this is the reason why I said classify, 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 classify. After I divided, because one of the major steps, like first steps for you to do when you're doing differential equations is to divide with whatever is in front of y prime. Because most of the functions start with y prime plus and then blah, the rest of the equation. So you take away whatever is in front of y prime in the first step, and then I decided not to try separation or anything like that because I see y over x and I see y over x squared. So I'm going to do this and then solve it for y, which is vx, and then find y prime, which is vx, sorry, copy v derivative of x plus copy x derivative of v. And now when I plug everything in, y prime becomes v plus xv prime minus y over x is v and minus v squared equal to 0. These v's die, and we are left with xv prime, and I'll ship v squared to the other side. And now you see that we can do separation of variable. We can separate now. So, or now we can separate. There we go. Leave my Yoda grammar at home. So we have x dv dx is equal to v squared. Ship all this stuff to the other side. We have dv over v squared is equal to dx over x. Hit both sides with the integral sign. The left-hand side becomes negative 1 over v when you integrate, and the right-hand side becomes ln of absolute x plus c. You need plus c on one of the sides. Now you send the minus sign to the other side and you flip. So this becomes v equals negative 1 over ln of x plus c. So if you flip one side, you have to flip the other side, and then the minus goes over, and this is what we have. Now, it's v, but we need this in terms of x and a y. So v gets replaced by y over x. So now this is y over x is equal to negative 1 over ln absolute x plus c. And to get a y of x as a general solution, you have negative x over ln absolute x plus c. And now you take the derivative, plug everything in. Yes, Gigi? I plugged everything in, so y prime is replaced with what y prime is, y over x, and this guy is replaced with v and v squared, which are these two guys. Now, most of the time it is, yes. Most of the time it is. It's just that that's how the simple problems work out for separation of variables later. But we did have examples where it was not. I believe when I taught the concept, only one example was y over x, and all others were something else. So, but probably homework was heavy on y over x. So sure. Are you happy with this? No. It's way too busy. Way too busy. That's my best definition of it. Way too busy. The standard trick is put it in the order of descending derivatives. Once you have your highest derivative first, divide it by whatever is in front of it, and see what that gives you. I would go as far to say that this over here gives away it screams substitution. Literally screams substitution. So this was the problem 3 out of those 30 problems on page 98, which I said you guys should work out and know. Well, Bernoulli's equation has this dx squared thing, right? Do you want to know that? I didn't put. Let me add on. So I should check on Evan's comment. Okay. No, he's right. It's too easy. All right. Any other questions? In his pajamas already.
We'll take care of him next time. Are you going to do social problems? Or all just change the value of the slope and then?
Yes, that's all it is. You keep changing the value of the slope, and then I believe, do they have any?
None of the homework in that section would actually help you.
Yeah, the homework gave you the actual graph, right?
Yeah, it was crap. I didn't even bother doing it.
Problem 34. It says solve in 2 ways. dy dx is equal to x plus 3y divided by y minus 3x. Jeez. Is there a way for me to... Ooh, there is a pause here. I never used this. Ooh. But it's live. That's the problem. But I can pause this. I can pause the. Not the stream, projection. Yeah, I can pause the projection. All right. So the goal over here is to. Yeah, I was just testing it. All right. The goal over here is to solve this problem in 2 different ways. Need to find analog pen so I can actually try this. What happened? I wouldn't say graphing. Did anyone figure out any of the ways? Cross. And then what do we get? Nice. So you already found the exact equations. Nice. And there it is. Way number one. I know you can't see it, but way number one, exact equations. All right, get cranking. Get cranking, exact equations.
Yeah, that's exactly how you see it. Yeah. When you do cross multiplication, right? You know how you have dy and dx now on either side, right? So now that makes is what you see, dy or dx. I love your question. Well, hey, they do equal, so that's good. Because there's a way you can see Dude, to be honest, like with these exact problems, there's literally a video online, and it cuts half the stuff out. It's like, oh, you could literally just like it's like a one-liner. Right, if I know how to integrate that, I know how to okay, you add those and then you add that on the bottom, you subtract them, and then boom, there's the answer.
Video on exact problem.
It's a video on exact problems.
Oh, you need enough for dy, you want particular. Like that. So what you're doing right now is checking for exact cases.
That's a good one.
That's just checking. That's just checking for the equal problem.
Did anyone figure out the second way? You were supposed to figure out the ways, and then we'll figure out the solutions. Substitution. What happened?
What did you say the second way is?
Substitution. So I worked out the basic of that substitution here. Now I need to do the integrals. There you go. So work out exact first, and then you already discovered that the second way is the substitution. Now I remember Alex solving the first time we seen a problem like this.
Divide by x.
Divide by x, yes. Okay, so we cross multiply. We have y minus 3x dy is equal to x plus 3 y dx. Then we bring this to the other side, and we have x plus 3y dx minus y minus 3x dy equals 0. But we don't like this minus here, so we shift that minus inside, which would actually swap the order of these two. So we have x plus 3y dx plus 3x minus y dy equal to 0. So when I take the minus sign inside, it changes all the signs. Great. So now the condition for exactness, we can call this one function f, we can call this one g, whatever. And what we need is the partial of f in respect to y to be the same as the partial of g in respect to x. Good. So partial on the first one is 3, partial on the second one is 3. They are the same, so equation is exact. Because equation is exact, we are going to take the first one over here, and we are going to integrate. So we are integrating x plus 3y dx, and we are going to get the x squared over 2 plus 3xy plus some function in terms of y. Now this is already our solution. I can call this f of xy as x squared over 2 plus 3xy plus c of y, and that's already our solution. But now I'm going to differentiate that in respect to y and set it equal to g. So when I differentiate this in respect to y, the first term dies, the second term becomes 3x plus c prime of y, and we set this equal to 3x minus y, which is from g. Now when you compare the two, 3x and 3x cancels, so we get c prime of y is equal to negative y. And if you integrate both sides quickly, you find that c of y is equal to negative y squared over 2 plus some constant c. And you already have the solution here, right? This was the partial solution. So now you just need to replace c of y with what c of y is, and you are done. So we have that the f of x y is equal to x squared over 2 minus y squared over 2 plus 3xy and then plus some constant c. You can say equal to 0. And that takes care of the solution. It's given in implicit form. You want a high five or you have a question? Oh.
When you after the first step, you use y minus dx dy with x plus dy dx. Couldn't you start checking for exactness right there?
What happened?
Scroll up all the way. Okay, first line on the solving tool.
Over here?
Yeah, couldn't you start solving?
If you try, you are going to get negative 3 equals 3. You have to have it in the form of exact equation. This is the form of exact equation. Yes. So when I integrated the first one, I found what I call the partial solution. Observe that that's that, right? I just copied it. So now this thing over here is already a partial solution. Because I need to determine this. C of y. So to find the C of y, I take the partial derivative of that. So partial derivative kills x squared because there's no y there. Over here, derivative of y is 1, so it's just 3x. And then derivative of C of y is C prime of y. So I differentiate it in respect to y. And once I differentiate in respect to y, I have that that's the partial derivative of y, but then we also have that this over here is the partial derivative of y. And you set them equal to each other.
Did we miss that day? I've been in a class. When do you know? I was going to ask about the partial derivative. When do you know when to take the partial? Like she was saying, you were integrating at x plus 3y dx. I didn't know right there you need to take the partial.
Because I need to set it up. Yeah, I need to set it up to set it equal to this.
You circle under G.
Yeah. And that's the blue stuff I wrote. And I said that's G. And once I set them equal, 3x cancels. You get the black equation here. Integrate both sides. And you get what cy is. And you just plug that cy in your partial solution to get your general solution. Now, if you're given initial conditions, you would go on to calculate initial conditions. Yes?
When you plug in the initial condition into that final equation?
Yes, to calculate C,
Okay.
if you have. Yes?
Are you going to integrate in terms of x and then differentiate in terms
If
of
it's
y?
possible, because it might be easier to integrate this in terms of y and then take the partial derivative in respect to x and set it to either one. So you can either go integrate first one in respect to x, because look, it's dx already, right? So if you just put the integral there, right, should be clear. And then you have a dy on this side. So if you integrate in x first, you take the derivative in y and you equal it to this y. If you start on this side integrating in respect to y, you take the derivative, you will actually obtain negative, you will obtain this first, and then by working it backwards, you would get that one eventually.
Technically, you can do whatever you want.
Yes, and well, I would say whatever the easier integration, right? Because one integral could be basic and the other one could be integration by parts. So why would you go to integration by parts if you can do the basic on dy?
Okay, I'm just saying.
Make sense?
Yeah.
Perfect.
He was just saying for this exam, he's saying.
No.
For the
In
exam.
general.
In general?
Yeah.
Oh, so that's in general. But what about now if you had to go back and check this, like you said? Is this one that you use to check to go backwards to get to the other way? Or
You can, yes, you can check this by using implicit differentiation. You do the implicit differentiation from Calc 1 on this answer, and then compare what you get to the original problem. That's not easy in this case, but algebra should be really long and tedious. Now, guys, this was the way one. They want us also to solve this in a different way. So, way two. Same problem. Y prime is equal to x plus 3y divided by y minus 3x. So, we can say by Alex, we divide numerator and denominator by x, and we obtain differential equation y prime is equal to 1 plus 3y over x divided by y over x minus 3. And again, you have this y over x screaming. So you v, I'm sorry, v equals y over x. So y is equal to v times x, and y prime is, copy the first, derivative of x is 1 plus copy x, and derivative of v is v prime. There we go. And now plug in. So instead of y prime, we are using v plus xv prime it's equal to 1 plus 3v divided by v minus 3. Is this correct? Yeah. Let's say it's good, right? We are going to subtract v on both sides and have xv prime equals to 1 plus 3v divided by v minus 3 minus v times v minus 3 divided by v minus 3 for common denominator. We have 1 plus 3v minus v squared plus 3v divided by v minus 3 as a common denominator. So xv prime is equal to, we have negative v squared plus 6v plus 1 divided by v minus 3. Move all v's to the left, so v minus 3 over negative v squared plus 6v plus 1 dv is equal to 1 over x dx, so dx over x. So separation of variables. And separation of variables is achieved by, right, you write v prime as dv over dx, and then you shuffle things around. Oh yeah, good luck with the integral here. Hello, Calc 2, right? So the first thing you should try is to factor out denominator. So I'm going to kick out negative 1 and have v squared minus 6v minus 1. And then we can unleash the quadratic to see what it factors over. Hopefully it factors, right? So that's going to be negative b, that's 6, plus minus square root of 36 minus and minus plus 4a, so plus 4 divided by 2. So it's 6 plus minus square root of 20. No, square root of 40, which is 2 root 10. I was about to do partial fraction decomposition. U sub. Yeah, why simple if you can complicate things, right? So u equals negative v squared plus 6v plus 1, and du is equal to negative 2v plus 6, all of that dx. I need to factor out negative 2 on this du, and it becomes v minus 3 dx. Nice. So I need negative 2 and negative 1/2 in front. Perfect. Negative 1/2, and then we have du over u equals to, on the other side we have ln absolute x plus c. Negative 1/2 ln of, and the u is negative v squared plus 6v plus 1 equals to ln of x plus c, and v is y over x, so negative 1/2 ln of negative y over x squared plus 6y over x plus 1 equal to ln absolute x plus c. Now what you can do is you can bring this half exponent inside, and then you can move the ln to the other side and combine the two ln's into one ln. So we have ln of 1 over, the stuff disappeared over here somewhere. There's stuff missing over here. Something is missing there. Integral sign, right? And a 1/2. So when I take this and I place it down, it has to be placed in the square root. So negative y over x squared plus 6y over x plus 1. And that's equal to ln x absolute x plus c. So actually, let me move this one immediately so I don't write it 15,000 times. Minus ln of x plus c. Sorry, equal to c. And now the subtraction of these guys is going to be the division. So I have ln of 1 over, and then I have x square root of negative y over x, everything squared, plus 6y over x plus 1 equals to c. And you see now this x can undergo the square root and becomes x squared and starts canceling these things, which is great. So ln of absolute 1 over square root of x squared goes x squared, kills this, so it's negative y squared. X squared on the other one becomes plus 6xy, and on the last one becomes plus x squared equals to c. Now we e both sides to kill off the ln, and we have that 1 over square root of negative y squared plus 6xy plus x squared is equal to e to the c. You can call, I don't know, put the letter mu, whatever. So move the square root to the other side. Mu times the square root of negative y squared plus 6xy plus x squared is equal to 1. Now you can move mu to the left hand side. So divide both sides by mu. And then square both sides to kill the square root. And you get negative y squared plus 6xy plus x squared is equal to, and you can call this 1 over mu squared, you can call it a new xi. There you go. So xi. And now, if you observe this carefully, look what you have. You have x squared minus y squared plus 6xy equals to this xi. And if you divide by 2, you get x squared over 2 minus y squared over 2 plus 3xy. You can move c on this side and call it plus c, and there is the same solution as before. I love differential equations. This is just... So next time someone in algebra tells you the problem is too long, Because all we did here is algebra. There you go.
That was just the second way, so you figured out, like they said,
Yeah.
to do the sub. But we were going for partial decomposition, and you stopped, no?
Yeah, well, they said use sub, and yeah, they were right. So we used these. Yeah. So it was a little bit of substitution, and then a little bit of use sub, and then a little bit of algebra, and there we go. Like, this is what you do on Sunday, you know, for a few hours. Yes. I'm sorry? It's actually a Greek letter. If you carefully write it. Well, I moved this to the other side and call it C. And because it was divided by 2, right? I divide everywhere by 2. So C divided by 2 was defined as negative C. Doesn't matter. They're called constants. Constants absorb everything. What do you need me to scroll up a little? You know what's going to happen if you ask for a little. That's it. Right there? This. E to the C. I define that as a mu. Because I need to define it as some other variable. And I didn't want to go with G's and F's and A's and B's. They're overused. Let's expand our... Evan has a question on the street. Yeah, to confirm that partial derivative and the integral with respect to other variable are equal to each other. Yes, he's being mad goofy, yes. Oh yeah, that's all he gets, streams within streams. But yeah, oh yeah, the troll says go home. So yeah, the reason you take the partial derivative of the other variable to confirm that the partial derivative of integrals with respect to the other variable are equal to each other. Now this is the exact equations. When we solve exact equations, so when you solve exact equation over here, you integrate the one that has dx, you integrate that one in respect to x, and then you differentiate it in respect to y because you need to equal it to this part of the problem. Those of you who took Calculus 3 already will recognize this procedure for obtaining the potential function in the section for conservative vector fields. I believe that's 14.3 or 14.4, 14.3 in your Calc 3 textbook. You have a two-dimensional and three-dimensional version. This is a two-dimensional version, the easier one. So you differentiate the first, integrate the first one, and then differentiate the answer in respect to y equally to the second one. Or as you guys suggested, integrate the second one, then differentiate the second one in respect to x equally to the first one to obtain c of x in that case. So it can be done in either way. Nice, you see? We practiced mostly algebra so far. And then I learned a little bit about u sub. Nice. Mu sub, yeah. So that was a nice question. I mean, you can't complain on that one. Of course you can complain, but it doesn't get you anywhere. So the only problems that we haven't, well, we did y cubed minus 1. So that was from chapter 2. Separable equations, we did that. First order linear, we didn't do integrating factor. We did substitution, we did exact, we did the word problems. We did the higher order, we did the third one. Constant coefficients, which is again the third one, and first order slope fields. So from the whole list, we didn't touch 3 concepts, and we only did 3 problems. Right? We did 3 problems, and out of whatever 10, 12 over there, we skipped on 3 concepts only. We can classify each one of these, obviously, and so on. So, great. Keep practicing, right? The slope fields, which is fast, we have only, what, 15 minutes or so? For slope fields, you know what to do. Or you will know what to do, I mean, depending on how much study time you invested. For slope fields, you pick slopes, you draw isoclines, and then put the little slopes on those isoclines, and you keep moving through the problem. So say you have y prime is equal to, let's say, 2x minus 1. Now, yes, this is differential equation that it's separable. You can do a whole bunch of stuff here. Actually, no, it's fine. Whatever. So this guy on here is actually slope m, right? And you pick that. Pick values. So the first time around, you say let m be 1, which means that your dy dx, which is y prime, is 1. If you pick that, you have 1 equals 2x minus 1, right? And then that's x equals to 1. So, right? So now you draw the isocline x equals to 1. X equals to 1 isocline is vertical line that goes through 1. And on that line, you get to put little 1 slopes. So 45-degree slopes along that line. And then you pick m equals to 2. M equals to 2, y prime is 2. You plug that in, and you get that this is 3/2. So x is equal to 3/2. When x is equal to 3/2, this is going to be really annoying to draw now, because the isocline is going 3/2, it's going really close to the previous one, only half a unit away. And the slopes that you are picking now are steeper because the slopes are 2. So you have to draw a steeper slope. It still increases.
The higher number of dy dx is the steeper.
Yes. So the next slope you pick is 3. So m equals to 3. So that means y prime is 3. So you plug that into differential equation. You get 3. So you get x equals to 2. So that isocline is, again, very close. And you have even steeper slopes.
Can it ever be vertical? Steep?
No, because that means it will be infinite, right? You would get equal, the slope that you pick is infinity.
Okay, now
right?
if it's a negative number, then it wouldn't be nearly as steep anymore?
Well, that's what we're going to check. So let's check m equals 0. So y prime equal to 0. So we have 0 is equal to 2x minus 1. And that gives us x equals 1/2, right? So isocline 1/2 would give us So isocline 1/2 give us horizontal slopes. I should have moved this. And then m equals -1. Y prime is -1. -1 is equal to 2x minus 1. So that's 0, so x equals 0. X equals 0 gets the slopes of -1. So isocline is this on the x-axis, and you have -1 slopes. So this looks like it's going to do this, right? It looks like it's going to do this. Now we can check this because we can solve the equation above and see what kind of function we get for up. Why up? You mean down?
Yeah, down.
Yeah.
Pages go down.
Oh yeah.
Oh, that's the younger one.
What was the equation? It was y prime 2x minus 1. So we have dy dx is equal to 2x minus 1. And you do separation of variables. You have the dy is equal to integral of 2x minus 1 dx. Wait, we're getting over here x squared minus x plus c. Why am I getting cubic equation there and I'm getting a quadratic over here?
Yeah, that should be made. So it should be a quadratic formula. So you have it going the same way as a positive slope.
At x equals 0.
At x equals 0, so you should change the slopes.
Oh, yes, I drew the wrong slopes. Okay, yes, yes, yes. I drew all of these slopes are. There we go. Thank you. Ah, blue. Witchcraft. There we go. What happened?
I think you should start all over again.
Yes, it's a -1 slope, so it looks like this. There we go. So we see it's a quadratic answer. And we see it's shifted, right? You can see that the quadratic answer is shifted because, right? Yeah, by 1/2. This will be on the test.
Sweet, and that's one problem. Yeah. No, I don't like that evil look.
Yeah. And then the next thing is use the slope fields to find e to the sine x minus 3. I mean y prime equals. All right. All right, so that's it for today. We'll work some more eventually.